Hey guys, what's up? Just want to give you a fair warning today. I don't have my microphone with me, so it might sound a little crappy. Hopefully not, but just a heads up. Hopefully you had a good weekend, a long extended weekend. I know we had some good times this weekend, so hopefully you did too. Hopefully everybody was safe and had fun and all that stuff. So anyway, let's get back to it today. 15.1 continued. We're going to start doing some symbolic integration. This is iterated integrals for double integrals. So iterated integrals. And no longer are we going to worry about Riemann sums. We're going to do iterated integrals. So what we're going to do is we're going to suppose f of xy is continuous, and we know what that means. So suppose f of xy is continuous on a rectangle, and we'll call that rectangle capital R. And we use a weird notation. We're going to say interval AB Cartesian product with interval CD. And all that means is the x variable and the y variable are in these intervals. So if we go back to our picture from last time, the interval AB is on the x-axis, interval CD is on the y-axis, and then the rectangle R is this orange box. So that is just a new notation for a rectangle. Interval CD. I know there's a lot of clicking because of the silly microphone inside the computer. So I'm writing on the screen, so try to bear with me. Hopefully it's not too bad. Okay, now integral from c to d f of xy dy means treat x like a constant. And integrate with respect to y. Integrate with respect to the y variable from y equals c to y equals d. And this is what we call partial integration. This is what we call partial integration. Because we're only integrating part of the variable, in this case the y variable. So partial integration. What's left then is a function of x. So this implies that the integral from c to d f of xy dy is a function of x. And we can call it something like a of x equals integral from c to d f of xy dy. And now that thing is actually a function of x. And if it is a function of x, we can integrate it with respect to x. Because we're only what's left? Okay. So now integrate this function a with respect to x. So now if we integrate a of x with respect to x, we would get integral from a to b, capital A of x, dx, which would equal integral from a to b of integral from c to d f of xy dy, and then we're integrating that with respect to x. And often we just write them the same size. Integral a to b, integral c to d, f of xy dy dx. And you kind of work from the inside out. So that tells you which bounds go with which variable. So the inner bounds go with the inner differential dy. So c and d go with dy, and then a and b go with dx. And this is what we call an iterated integral. So this is an iterated integral. Well, that's great, but how do we know if that's actually the value of the double integral that we defined as the limit of Riemann sums last time? So this is all well and good, but how do we know if that's the right thing? Is that how we actually calculate a double integral symbolically? Well, there's something called BeNice theorem. So BeNice theorem BeNice theorem says, suppose that f of xy is integrable, which really just means that there's a finite integral as a limit of double Riemann sums. So we'll just say f of xy is integrable over the rectangle R. So some rectangle capital R, where R is defined, I'll use the set notation, all ordered pairs xy such that A is less than or equal to x, less than or equal to b, and c less than or equal to y, less than or equal to d. So suppose f of xy is integrable over the rectangle, then the double integral over R, the capital R rectangle, f of xy dA can be calculated as an iterated integral, integral from a to b, integral from c to d, f of xy dy dx. Or you actually can also calculate it as integral from c to d, integral from a to b, f of xy dx dy. So BeNice tells us two things. The first is the double integral can be calculated as an iterated integral. So number one, double integral as defined by limit of a double sum can be calculated by an iterated integral and number two, the order of integration doesn't affect the value. So there are two things that BeNice theorem is telling us. So, now I guess all we need to do is look at some examples of how to do iterated integrals. Looks like we still have a little bit of a lag again today. I'm not sure why that is. I have everything closed. Let's see if something running in the background. Okay. Well, let's look at a ton of examples. We're going to do like 6 to 7 or 8 examples here. We'll see. And call it a day. Not sure why there's such a big lag. Okay. Example. Let R equal rectangle where x is from 0 to 2. And y is from 1 to 4. And then evaluate double integral over the rectangle R. And the function is 6x squared plus 4x y cubed dA. So let's evaluate this double integral as an iterated integral. So we can pick either variable to integrate first. So for BeNice theorem says the double integral over the region R, and then our function is 6x squared plus 4x y cubed dA. For BeNice theorem tells us that we can choose to do either x first or y first. So let's just pick one. I guess we'll do maybe x first. And so that will be the integral from 1 to 4 for y, integral from 0 to 2 for x. And I write the x bounds on the inside because I'm going to do it first. And then the function I want to integrate is 6x squared plus 4xy cubed dx and then dy. Now, integrate from 1 to 4. And now, if I have 6x squared and I want to integrate that with respect to x, I would do 6 over 3 x cubed, which is 2x cubed, plus 4 over 2x squared y cubed. So that's 2x squared y cubed, because I treat y like it's a constant, evaluated from x equals 0 to x equals 2 dy. So we integrate the terms here, this one would be 6 over 3 x cubed. And this would be 4 over 2 x squared y cubed. Y cubed is just treated like a constant. But don't even worry about the y, it's just like a constant. Okay, so just polynomial here, not too bad. Plug in the bounds. I'm going to have integral from 1 to 4. Now if I plug in the bounds for x equals 2, I get 2 times 8 plus 2 times 4 y cubed minus 0 dy, which equals the integral from 1 to 4, 16 plus 8y cubed dy, which will be, integrate that with respect to y, we get 16y plus 2y to the 4 from y equals 1 to y equals 4. And for these, I like to write the bounds as x from x equals 0 to x equals 2, and then here from y equals 1 to y equals 4. That way I just don't forget which variable I'm plugging in the numbers to. So, I mean, at this point, it's obvious. I only have y left, so I'm plugging in the bounds for y. But just to be careful, I like to write the bounds this way. And now I can plug in the bounds, and this will give us 16 times 4 minus 1 plus 2 times 4 to the 4, 4 to the 4, minus 1 to the 4. And so that's 16 times 3, which is 48, plus 2 times, see, 4 to the 4 is 256, 256 minus 1. And I do believe this turns out to be 558. So 512 minus 2 is 510, yeah, 558. And that is our answer. Yeah, the stream was buffering pretty bad. I'm not sure why it was lagging, but I think it's a little bit better now from what I can see. Let's see. Let me know if there's more trouble. I'm trying to watch it myself. It did look like it was lagging pretty bad, but I think it's a little bit better now. Cool, cool. Questions? We'll move over to another example here. See if there are any questions in the meantime. I'll just go ahead and write this example down. Example is evaluate integral from 4 to 5, integral from 3 to 4, integral from 3 to 4, 1 over x plus y squared dy dx. So if we were going to do an integral, if we had something like 1 over x plus 2 squared dx, we would use a u sub. So we would do a u sub. U substitution, where we would let u equal x plus 2. And then du would be dx. So basically, if we had like a variable plus a constant, we would do a u sub to evaluate this integral. Well, that's exactly what we have here if we're considering y to be the variable and x to be the constant. So let's do a u substitution to basically turn this into 1 over u squared. So we're going to let u equal y plus x, where x is treated like a constant. So where x is treated like a constant initially, right? Because we're doing y first. Whoops, sorry. So where x is treated like a constant initially. Then du would be dy. If I just differentiate with respect to y and treat x like a constant. So then, if y is equal to 3, u would be 3 plus x. And if y was equal to 4, u would equal 4 plus x. So making all of these substitutions into our integral, we get the integral from 4 to 5 for x, integral from 3 plus x to 4 plus x for y, and then 1 over u squared du dx. So basically we eliminated the y variable and turned this integral into only terms of u. And now we know how to integrate 1 over u squared. That's negative 1 over u. So this is going to be integral from 4 to 5, negative 1 over u from u equals x plus 3 to u equals x plus 4 dx. And then plug in these bounds. Get, this is going to be the integral from 4 to 5 for x, negative 1 over x plus 4 minus negative 1 over x plus 3 dx, which is integral from 4 to 5, 1 over x plus 3 minus 1 over x plus 4 dx. And now how do we integrate these two? I guess technically it's like a little u sub for each expression. U equals x plus 3 and then u equals x plus 4. Or if you don't want to use the same letter, we could use something else like w for one and v or something for the other one. So, but it's just going to be natural log. So this is going to be natural log absolute value x plus 3 minus natural log absolute value x plus 4 from x equals 4 to x equals 5. So that will be natural log of 8 minus natural log of 9 minus natural log of 7 plus natural log of 8. And I believe log rules will tell us this will reduce to natural log of 64 over 63. So we have 2 times natural log of 8 minus natural log of 63 after using some log properties there. So any questions? try to take a minute, see if there's anything that you guys have questions about. Looks like the lag is pretty much gone. Hopefully it'll stay gone. Looks okay. Let's see. Just write down a property, which is really nice. Nice property. If f of xy is what some people might call separable, you could just say it's a function of x times a function of y. So if your function f of xy is just really a product of functions of x times function of y, then the double integral is integral from a to b, integral from c to d, f of xy is equal to, or dy dx is equal to integral from a to b g of x dx times integral from c to d h of y dy. But it's only in the very special case of f of xy equals a product of function of x times function of y. So it's a very, very special case when this happens. It's not always going to happen. Just sometimes it does happen, and you take advantage of it when it does. But you can't like bank on it always happening, so just be careful. Make sure that what you're trying to do applies to the situation. For example, just to an easy example first. So this easy example is a double integral over a rectangle R sine x cosine y dA, where R is equal to interval 0 to pi over 2, Cartesian product with interval 0 to pi over 2. So evaluate this double integral. And to do it, we can just use this property. So note f of xy equals sine x cosine y is of the form g of x times h of y. And g of x is sine x, h of y is cosine of y. So that tells us double integral over the rectangle R sine x cosine y dA could be represented as integral 0 to pi over 2 sine x dx times integral from 0 to pi over 2 cosine y dy. So you can break it up as this nice product of integrals and integrate. So integral of sine x, or antiderivative of sine x, is negative cosine x from x equals 0 to x equals pi over 2 times integral of cosine, or antiderivative of cosine, is sine y from y equals 0 to y equals pi over 2. And evaluate those, we get, see, negative cosine of pi over 2 would be negative 0 minus negative cosine of 0, which is 1, times sine of pi over 2, which is 1, minus sine of 0, which is 0. So this is just 1 times 1, which is 1. Not too bad, really. Just you have to remember our antiderivatives. That's going to be super important. Also, we're going to need to know our techniques of integration pretty well. It's going to be extremely important to go through these double and triple integrals. And when we eventually get to chapter 16 at some point, then we're going to need to you got to be really good at integration. Integration is so important. Let's look at some more examples. Example, evaluate integral from 0 to 1, integral from -3 to +3, and then the function is xy squared over x squared plus 1. And those are dy dx. Right, so this function, xy squared over x squared plus 1, is one of those functions that you can separate. It's separable, we'll call it. And you could say it's x over x squared plus 1 times y squared. So it's a separable function. And if it's a separable function, we can say that the integral from 0 to 1 x over x squared plus 1 dx times integral from -3 to 3 y squared dy. So I can separate the variables like this, which is really nice. Let's see, the first integral, I need to do a u substitution. I'm going to do a u substitution. U equals x squared plus 1 du equals 2x dx. And if x equals 0, u equals 1. If x equals 1, u equals 2. So this is going to be integral from 1 to 2, 1 over u, and then du over 2, times 2 times integral from 0 to 3 y squared dy. Because it's an even function over a symmetric interval, we can actually multiply by 2 and integrate from 0 to 3. So we'll use that property there. And now, this is really nice, the 2's can cancel here. So don't even worry about the 2 anymore. This is going to be natural log of u, absolute value from 1 to 2, times y cubed over 3 from 0 to 3. So this is going to be natural log of 2 minus natural log of 1 times 27/3 minus 0. And what do we know? We know natural log of 1 is 0. So this is going to be natural log of 2 times 9. So 9 times natural log of 2. Or, I guess you could say it's natural log of 512. Either way. I'd probably leave it as 9 natural log of 2. Or raise 2 to the 9th power, which is 512. Either way. Okay, we got another example here. This example says evaluate integral from 1 to 5, integral from 5 to 6, xy e to the x plus y dy dx. So I think what I'm going to do is actually do some algebra first, because it's actually separable. After we do some algebra, we can see that it is separable. So x times y e to the x plus y is actually x times y e to the x times e to the y. So we can write this as x e to the x times y e to the y. So it actually is separable. So f of xy is separable. That means we can integrate it from 1 to 5 for x e to the x dx, times integral from 5 to 6, y e to the y dy. So let's just go to the side and do an integral t e to the t dt, because that's basically the same integral that we have over here, x e to the x dx and y e to the y dy. It's really the same integral, just different bounds. So let's integrate t e to the t dt. So I'm going to do u equals t dv equals e to the t dt. I have to do this by parts, and so du equals dt and v equals e to the t. And our formula is uv minus integral v du. So this is going to be t e to the t minus integral e to the t dt, which is t e to the t minus e to the t. So that is going to be our integral, regardless of the variable there. So this is going to equal x e to the x minus e to the x from x equals 1 to x equals 5 times y e to the y minus e to the y from y equals 5 to y equals 6. So that was nice. in that both integrands were exactly the same function. So we could just do the integral or the antiderivative once and then plug in different bounds. And as we plug in the bounds, we'll see that we get something like 5 e to the 5 minus e to the 5 minus 1 e to the 1 plus e to the 1 times 6 e to the 6th minus e to the 6th minus 5 e to the 5 plus e to the 5. Simplify anything that we can inside the parentheses. So this e to the 1 and this e to the 1 cancels. And let's see what we get now. So in the first parentheses we get 4 e to the 5 times the second parentheses we get 5 e to the 6th minus 4 e to the 5th. Now distribute what we have and we get 20 e to the 11 minus 16 e to the 10. And that is our answer. Any questions? Give us a minute to catch up and slow down just to make sure everybody's on board. Got two more examples here. I think we'll do both of them. They're a little bit trickier though. I mean, not too bad. But let's run through them. So this is just going to be a couple of other examples. May or may not actually be separable. They're just a little bit harder. So this first example, integral from 1 to 4, integral from 1 to 2, x over y plus y over x dy dx. I guess we'll do y first since it's already set up that way. So if we integrate y, this will be the integral from 1 to 4 and x natural log absolute value of y plus 1 over x times y squared over 2 from y equals 1 to y equals 2. So the trickiest part is just like thinking about what the antiderivative should be for y and leaving x as a constant. So just keep that straight in your brain and this problem is really not too bad. So now we have to plug in these bounds for y, and that will be integral from 1 to 4 for x. And plugging in the bounds we get x natural log of 2 plus 1 over x times 4 over 2, and then subtract x natural log of 1 minus 1 over x 1 over 2 dx. And simplify, what do we get? Well, we know some things like this natural log of 1 is 0. So let's simplify the integrand before we do it. So integral from 1 to 4, x times natural log of 2. And now we have 1 over x times 2 minus 1 over x times 1/2. So it's going to be 3 halves. So plus 3 halves times 1 over x dx. And now integrate with respect to x. So we get natural log of 2 over 2 x squared. We'll say that from 1 to 4 plus 3 halves times natural log of absolute value x from 1 to 4. This will be natural log of 2 over 2 times 4 squared is 16 minus 1 squared plus 3 halves times natural log of 4 minus natural log of 1. Again, natural log of 1 is 0. So this is going to be 15 over 2 times natural log of 2 plus 3 halves times natural log of 4. And what can we do? We can actually do a few log rules. We can say this is going to be 15 halves natural log of 2 plus 3 natural log of 2. Since 4 is actually 2 squared, and I can pull that squared out front of the log and cancel with the 1/2. So 15 halves plus 3 would be 21 halves. So we can really write this as 21 halves times natural log of 2. Just to use some more log rules to simplify. That's our answer. And I have one more example here I think would be good. And it says evaluate integral from 0 to pi, integral from 0 to pi over 2, cosine of x plus 2y dy dx. So there are two ways to do this. Well, I'm sure there are more ways, but two ways that I would want to show you. The first one we've already seen is like a u substitution. Could do u equals x plus 2y and treat y like the variable and x like a constant. So we could do it that way. Or we could actually use a trigonometric identity. So there's two ways. The first one would be u sub, but we've already seen one of those today. So I'm going to use a trig identity to simplify. Well, I say simplify, it actually is going to look more complicated after we get going, but oh well. So I'm going to do the trig identity. So my approach here will use cosine of a plus b equals cosine of a times cosine of b minus sine A sine B. So I'll do the trig identity approach. Basically, A is x and B is 2 plus y. So we're going to change this to be the integral from 0 to pi, integral 0 to pi over 2. And this will turn into cosine x, cosine of 2y, minus sine x, sine of 2y, dy dx. Now, just integrate with respect to y. So this is going to be the integral from 0 to pi. And integrate with respect to y. Well, cosine x is like a constant. Integral of cosine 2y is going to be 1/2 sine of 2y. And that's going to go from y equals 0 to y equals pi over 2. Minus sine x is like a constant. Integral of sine of 2y is negative 1/2 cosine 2y from y equals 0 to pi over 2, and then dx. So now plug in the bounds. Integral 0 to pi cosine of x times 1/2. And then sine of 2 times pi over 2 is sine of pi, so sine of pi minus sine of 0, both of which are 0. So that's 0, this is 0, that's nice. Minus sine x times 1/2, oops, negative 1/2, so I'll just make this negative 1/2. That's confusing because it looks like sine x. Well, sine x times negative 1/2. And then cosine of pi minus cosine of 0 dx. And these, well, this is negative 1 and this is 1. Simplifying everything, get integral from 0 to pi over 2. So negative negative is positive 1/2 sine x times negative 2 dx. So this is going to be negative integral 0 to pi, sorry, not pi over 2. Integral 0 to pi of sine x dx, which is cosine x from 0 to pi, which is cosine of pi minus cosine of 0, which is negative 1 minus 1, which is negative 2. Any questions? If not, I'll call it a day. I think we've done quite a few examples today, so that helps out a lot, I think. We'll call it a day. If you do have any questions, you can hang around, ask them in the chat. I'll be here. If not, have a good rest of your day. I'll see you next time. Talk to you later.